This presentation will show you how to do program generation with template processing. So here's the scenario. So we've got some final state machine and we want to generate C code from it. The idea is that we might want to run this C code on some target hardware rather than executing in some way the final state machine directly. So the program generator that I want to present here is going to use template processing. That's going to be the interesting bit. So here's a sample final state machine. It describes a turnstile as it's used in a metro system. So we've got a state like locked for the door being locked, and someone might insert a ticket and the ticket then gets collected. And this is how we end up in the state unlocked, and then someone might be able to go through by pass. So if someone though tries to go through in a locked state, then an alarm would be triggered. So we've got states, events and actions, and the ages are the transitions. So this is the kind of C code we want to get. We've got an enum type for all the states, another enum type for the events, and we also record the initial state, which was like marked here by this gray color. So we've got a list of C functions for the actions, and we've got a function next that is modeling all the transitions. Given the current state and an event, we'll return a new state, and along the way by this switch case logic here, we might also execute the functions for the actions. So in Grammarware speak, we would maybe parse some textual representation of the final state machine. Then we would get some AST or CST, abstract or concrete syntax tree, describe a translation to some intermediate representation that is closer to the C code that we want to get, and perform some formatting to get the actual C code. In modelware speak, we also essentially parse, but we call it text to model transformation, and we get some model, and we perform a model to model transformation again to get closer to the C code, and we perform a model to text transformation to get the actual C code. Okay, so we somehow need to represent the final state machines in our program generator. So we opt for Java this time around, and this would be essentially our object model for final state machines. It's of course very much simplified. So a finite state machine breaks down into a list of states and into a list of transitions. A state is just the state idea and an indicator of whether this is the initial state. A transition has a source and a target state, and it also associates with an event and an action. So this is how we could construct maybe the turnstile FSM in the Java code if we assume that we have a fluent API on top of the object model that you just saw. So we use nice method chaining and all this to construct an object graph for the turnstile FSM. Now we want to use template processing to generate C code for finite state machines, and here's the hello world of template processing. A template is essentially just text with some parameters in that. So here's the hello name template, and this Java code fills in the parameter name with the text world, and then runs the rendering method of the string template library to render the template. So we get this text of the rendering. So there's lots of template processors out there. We are going to use string template, which is like a mainstream option in the Java platform. So rather than showing you immediately all the templates that we need for the example at hand, here's an outline. So we need a bunch of templates. We need a main template parameterized in all the states, in the initial state, in the collection of events, collection of actions, and in the transitions, but this time grouped by source state, because this is how we need to generate code, that we group all the transitions in one switch case statement per source state. Okay, we need an auxiliary template, or at least we can use one to factor out the code for the methods or functions that represent actions. And we also have a helper template that deals with the transitions per state, and also a helper template just for the code concerning one individual transition. So you already see that we essentially use some equational notation here to define templates, and that we use different brackets for enclosing the content. So when we enclose the content of the template into double quotes, well, that's the simple case. When we need multi-line templates, then we use the double angle brackets, and this also implies that all the indentation, all the line breaks in the multi-line template content, they are transported into the generated text. So if you need multi-lines but we don't care about indentation line breaks, then we use this specific form here. As we just saw in the Hello World example, we can refer to parameters within templates, but we might also touch some additional information about formatting, such as formatting the parameters text in uppercase. And if we have a parameter that is essentially a collection, then we can also control how the individual elements should be separated. In this case, we want them to be separated by comma. We may invoke other templates from within a template. So in this case, we say we want to invoke template temple on the parameter p. We may also project parameters to some properties or fields, and we may also use conditionals within templates. So here's the complete definition of the templates in the running example. Let's not get lost in details too much here. So you see here, for example, we have the part that deals with the enum type for states, or here for events, or here we invoke the template action on the parameter actions to deal with the to generate functions for the actions. And here we have the big switch case, and we invoke the template t group on the parameter t groups to generate all the blocks of code for the various possible source states. This is how the code template looks like for the action functions, and this is how the code template looks like for the switch case per state. And here's how the code looks like for the individual transitions, and we also use some conditional here to only invoke an action function if there's action associated with the transition at hand. And you see that in a few places we invoke upper and lower to sort of normalize the names in the generated code. Okay, we also need to write some Java code to actually fill in the template and to build up the data structure needed for the parameters. So in this case, it's going to be really simple. So okay, we need some helper class here for the group of transitions, group by state ID. Very simple class that we're going to use down here. And then we have some segment of code that indeed builds up the collection of states, events, actions, and groups of transitions. We look at this in detail in a second. And down here, we just have some boilerplate text that fills in the parameters and invokes the rendering process. So the somewhat interesting Java code in this example boils down to this sort of mapping, building up the collection states, events, actions, and T groups from the incoming finite state machine. So this is all very simple. So here we just loop over the states in the finite state machine, and we add an undefined state because the generated code relies on an undefined state. And here we build up the collection of events by basically going over all transitions and extracting all events that ever occur, and we need to use a set because of course events may occur many times. Likewise, we extract the actions from the transitions. And as to the groups of transitions, well, we use this auxiliary type of groups of transitions. So again, we go over all the states in the finite state machine, and for each state we go over the transitions, and we include all the relevant transitions that have the source state that we want for this particular group. Okay? This is all the code we need to write to translate the finite state machine into the data structures that are needed for the template rendering process. So let's wrap up. Here's a list of issues that you should keep in mind when you develop your own template processor. So I point out escaping, indentation, and all kinds of formatting that you want to control. So overall, each template processor is different and comes with a very specific notation, or you might say idiosyncrasies. So the key design challenge in developing a template processor is really coming up with the mapping of the primary data structure to the data structure that you can actually use for driving the template processing process. So that's it. So all the code is online, and by the way, this material is also further discussed in the software language book.